started, welcome to G1. We're going to start off this semester with a couple of lectures from Gammage, who agreed to do a mini course explaining basically the basics on stock wrapped Fukaya categories and his view on the subject. Please ask questions. Please treat it as a training session. So just try to imagine actually using this material in your projects. I know a lot of you should use it. So, don't be afraid. Thanks.
Thank you. Well, thank you for inviting me to talk. I said this before, but I haven't prepared that much actually, material, so to speak. So I'm hoping that this will be that people will interrupt me with questions and we'll go on digressions and so forth. So I'm told that the format is we go to 3 and then there's a break and then there's more questions and discussion afterward. Is that roughly? Okay. So I guess this talk is supposed to be, yes, an introduction to wrapped Fukaya categories. Part 1. So there's sort of a canonical reference now for the theory of wrapped and partially wrapped Fukaya categories, which is this series of 3 papers by Ganatra, Pardon, Shenda. The first one gives the sort of basic definition of the wrapped Fukaya category of a Liouville sector. I'll say what a Liouville sector is in this talk. That might be all I say. The third one sort of proves that category is equivalent to constructible sheaves or microlocal sheaves, so it sort of tells you how to compute it. And the second one is sort of where the meat of all the structural results are. So kind of, I would say that number 2 in this paper, which is the one titled which is the descent, something about descent is the sectorial descent for wrapped Fukaya categories. That's the one where most of the structural results are proved. And so that's the one that I'll be sort of maybe talking about most today and next time, although I hope to sort of eventually give some constructible sheaf calculations. Maybe I'll keep this open in case I need to consult it. So the second sort of caveat at the start of this talk is that I might not get to very much about the wrapped Fukaya category today. A lot of this talk is going to be about setting up the geometry that we are interested in studying. I don't know what everyone's background is, so let me sort of start by saying that what we're interested in this talk, so the starting point for sort of the whole theory at this point is going to be the theory of Liouville sectors. So the main sort of part of, at least the first part of this talk, is going to be teaching you not exactly what a Liouville sector is, but I'll give a sort of approximate definition of a Liouville sector. Yeah, I'll give a sort of approximate definition of a Liouville sector, and we'll see why those are kind of the important things to consider here. So let me remind you that a Liouville domain is a particular kind of symplectic manifold, and it is a compact exact symplectic manifold with boundary. So the word exact here tells you that the cohomology class, that this symplectic form, so this is the symplectic form, and the word exact here tells you that that form is exact. So omega is equal to d lambda for some one form lambda, which is the Liouville one form. So this is an exact symplectic manifold with boundary with a condition such that the Liouville vector field so remember that the Liouville vector field, so I'll give this thing a name, say Z. So by definition, the Liouville vector field is where omega is a symplectic form, which means that at every point it gives you an equivalence between one forms and vector fields. Right? If I plug in a vector here, I get a one form, and what it means to be symplectic is that correspondence is non-degenerate, which means it has an inverse. So I can take the one form lambda and get a vector field out of it. So equivalently, the Liouville vector field is a vector field which dilates the symplectic form in the sense that the Lie derivative of the symplectic form with respect to this vector field is equal to the symplectic form. This is just, if you can just apply Cartan's formula here using that d omega is equal to 0. Right, so this tells you that since d omega is equal to 0, this Lie derivative has to be equal to d of the inclusion of z into omega, which by definition is lambda, and d lambda is equal to omega. Okay, so I didn't finish my definition, such that the Liouville vector field is outward pointing, maybe outwardly transverse to the boundary of M. Okay. So maybe here is a picture of an example. M equals T star S1. And my Liouville vector field, I'll say this more in a second, but the Liouville vector field, since I said this is a compact symplectic manifold with boundary, I guess I should take my, let me put it this way. I can take M to be D star X, where by D star, I mean the unit disk, cotangent disk bundle of X. So cotangent disk bundle. So what I mean is the cotangent bundle is some vector bundle on X, and instead of taking the whole vector space, I take like a unit disk in each fiber after putting a metric on it. So then I get a symplectic manifold with boundary. So in this case here, I get this as S1 times the interval -1 to 1. And of course, on the cotangent bundle, I have my canonical symplectic form. Omega is sum of dp dq. Lambda is sum of p dq. And then my vector field, then z, is sum of p del p. So it's the sort of Euler vector field where q are the position coordinates in the base of M, and p are the momentum coordinates in the fiber. So p del p is this Euler vector field that dilates you out, scales the fibers out. So you can see that here in this picture, I'm outward pointing everywhere on the boundary of my manifold. Yes, so this is one canonical example. Maybe let me give you one other example, which is also very important, which is where M is the 2n dimensional ball or disk. So here, the symplectic form, I mean, the Liouville vector field I can take to be actually, I mean, I could take this, of course, I could take my Liouville vector field where I look like the, I could take this to be like 0, 1 times 0, 1 or something, or I can take this to be the, or I guess that's a Liouville sector, so I can't do that yet. Okay, so I'm going to take my radial Liouville vector field here. So it's again just going to be this vector field that's pointing outwards like this. Okay, so those are a couple of examples of Liouville domains. So what you should always keep in your head is that usually when people write down a Liouville domain, it's in order to control the behavior of a Liouville manifold. So a Liouville manifold is obtained by taking a Liouville domain and just cylindricalizing, just adding cylinders at the end, so it becomes no longer, so maybe I'll say a Liouville manifold, a sort of finite type Liouville manifold anyway, is M union boundary of M times R. So this is the cylindric, whatever. This is the cylindricalization of the boundary. So what that means is that kind of like on this picture, if once I know what this thing is, I can just add a sort of infinite cylinder here to get back to example. The whole cotangent bundle of M in this case, or in this case, like R to the 2n. So you should imagine that whenever I write down a Liouville domain, I'm just saying like I have a Liouville manifold and nothing interesting is happening outside of some compact set. I have this compact set and then the Liouville vector field is just kind of like scaling so that outside that compact set, everything looks exactly identical to like what was happening near the boundary, but scaled up. Okay. Any questions about this? This is just the sort of starting point. I haven't hit Liouville sectors yet. Just want to make sure that everyone's on the same page.
That like the optimization of the top search that you have on the phone.
Yes, correct. So so this is an exact symplectic manifold. So the restriction, I'll say this again in 1 second, the restriction of this to the boundary is a contact structure. And then this thing has a natural form that's lambda wedge dt, where t is the coordinate here. So that makes this symplectic and makes the Liouville vector field just sort of get bigger and bigger the farther out you go. So again, this is just a way of sort of like saying that a Liouville manifold is the cylindricalization of a Liouville domain, which again means that you take this thing and then you take the symplectization of the boundary and glue it on, is just saying that like whatever's happening on my manifold is controlled by something in some compact set. So that's all I need to consider. Okay, so yeah, so since M, so if M is Liouville, this implies that the boundary of M equipped with form lambda is contact. So the boundary of M is now a 2n minus 1 dimensional contact manifold. Right, this means that lambda wedged with d lambda to the n. So what does it mean to be symplectic? It means that omega to the n is non-zero. And so to be contact means that lambda wedged with omega to the n minus 1, or lambda wedged with d lambda to the n minus 1 is non-zero. So you get a maximally, maybe I'll just say that it's contact, i.e. lambda wedged with d lambda to the n minus 1, non-degenerate. So you get a maximally non-integral thing. And recall that a Legendrian in here a Legendrian submanifold in the boundary of M is a submanifold or something with I guess the simplest way to say it is that lambda is an n minus 1 dimensional submanifold with lambda restricted to submanifold L with lambda restricted to L is equal to 0. Okay. Yeah, so what do I want to say? Did I get my numbers right here? Yeah, I think I did. Since this is 2n minus 1, this should be an n minus 1 dimensional thing. Yes. Okay. So for our purposes, this is not actually the complete definition, but it's going to be good enough for the things that we are going to talk about here. So for our purposes, a Liouville sector is determined by the data of M, a Liouville manifold, maybe a Liouville domain, together with a Legendrian in its contact boundary. Okay. So what you are supposed to imagine is that really the actual thing that people call a Liouville sector, I don't know, there's various kinds of names. Really, you should imagine that the thing people call a Liouville sector is what you would get if you, maybe I'll say this, idea is that, okay, so if someone gives me a Liouville domain without any choice of Legendrian in the boundary, then I said that I have this sort of completion. Maybe I'll give this, well, maybe I won't give a name. I have this sort of completion of M where I just glue on cylinders here. And so the idea is that if someone gives me a Liouville domain with a Legendrian in the boundary, then the Liouville sector is obtained by completing M away from lambda. So you should think of a Liouville sector as a manifold with boundary, and the boundary is precisely like a little neighborhood of lambda. So I'll give some examples in a moment. So example, when n equals 1, okay, so M is a 2n dimensional manifold. So in the, okay, if M, okay, well, if n is 0, I guess that's sort of pointless because there's no boundary to speak of. So, okay, so this is the simplest case we can think of where you actually get a Liouville sector. So when n equals 1, right, a Legendrian is just a 0-dimensional submanifold. Lambda, I mean, and there's no further condition on being Legendrian besides being a 0-dimensional submanifold. So when n equals 1, lambda equals lambda equals any 0-dimensional submanifold of the boundary of M. So e.g., so I had this case of T star S1, which is my favorite one-dimensional symplectic manifold, and I can just take lambda to be some collection of points in the boundary. So this is my lambda, right? And similarly, I could take the disk, and once again, I could take some collection of points in the boundary. So these are sort of the one-dimensional, these are some examples of one-dimensional Liouville sectors. Any questions about these definitions so far? Yeah. Right. So what I mean, yeah, so let me explain that in a picture now. So what I mean is that I take a little neighborhood of lambda. I don't know if I'm going to have time in this lecture to discuss the notion of a Lagrangian skeleton, but you can imagine that like lambda is a little skeleton of its neighborhood. I mean, if lambda is smooth, if lambda is a smooth Legendrian, okay, I know I said my Legendrian was a submanifold, but I actually want to allow much more general things than submanifolds, but whatever. If lambda was a submanifold, then it has a little neighborhood that looks like its cotangent bundle. That's like a version of the Weinstein neighborhood theorem. And so in this case, I have these little like neighborhoods here. And the idea is that what I'm going to do is that like away from those neighborhoods, I'm going to do this completion that I said before. And over here, I'm just not going to complete there. So I'm going to still keep this like boundary part of this disk here. So what I'm going to get is something like this, where kind of, let me give a different color to these strips here. So sorry, I guess the blue is actually not that different than the white. But the idea is that the blue bits are the boundary of my Liouville sector. And that on these bits here, I've done my cylindricalization trick. So the idea is that like originally, I had this Liouville vector field that was kind of outward pointing everywhere. So over here, yeah, my Liouville vector field is kind of looking like this, like it did before. But I've sort of modified my Liouville vector field in a neighborhood of these guys so that it looks more like the cotangent Liouville vector field of this guy. So here I've kind of turned around my Liouville vector field near these guys. I'll discuss the Liouville vector field more in a moment. But the basic idea is that now a Liouville sector is kind of a manifold with boundary where the boundary is a neighborhood of the Legendre. Is this picture sort of legible to people? Other questions about this kind of definition? Okay. Somehow, yeah, it's very important. These are, I mean, let me say this. These are the basic building blocks of Liouville geometry. So, yeah.
Just not sure on the terminology. Is that a Liouville sector or a Liouville manifold? Fill in the non-neighborhood parts with
This is a Liouville sector. So I said the Liouville sector is what you get if you sort of take a Liouville domain and you specify this Legendrian submanifold. So strictly speaking, the Liouville sector is the like manifold with boundary you get by doing this completion away from a neighborhood of the Legendrian. I'm maybe not going to worry too much about, these distinctions because like, you can kind of like, for instance, the translation between Liouville domain and Liouville manifold we saw as like pretty obvious. You just kind of like glue on a cylinder at the end, or you just restrict to a compact thing that contains all the information. And like something similar is kind of happening with the Liouville sector. You can do this thing where you complete away from the stop, or you can just kind of remember that you had the stop and that you were going to do some operation there. So these are the basic building blocks of Liouville geometry. I should say, okay, actually, technically, I'm really more interested in Weinstein manifolds than Liouville manifolds. I'll just say there's this, I'll say this because I'm about to say Weinstein's name, so I may as well say what a Weinstein manifold is. I'll say that a Liouville manifold is Weinstein if the Liouville vector field Z is gradient-like for an exhausting Morse-Bott function. Basically, this condition does is it guarantees you that your Liouville vector field is not doing anything too crazy. So all the Liouville manifolds that you're likely to encounter in life are going to be Weinstein if you're, I don't know, at least in my line of work. And all the pictures I'm going to draw on the board are certainly Weinstein. Like this vector field is clearly like the gradient vector field of the function that's just like norm squared, distance from the origin. And similarly for a cotangent bundle, the standard Liouville vector field is like the gradient of the like norm squared in the cotangent fiber function. Anyway, this is just to say that like there's certain theorems that are slightly better stated for Weinstein manifolds, although actually you need a little bit less than Weinstein. You just need something about the skeleton being sufficiently isotropic. Basically, like maybe I won't go into it now, but I'll just say this is some niceness condition on vector fields. Okay. So what do I mean by saying that these are the basic building blocks of Liouville geometry? Basically, how did they get the theorem? How did these guys get the name Weinstein manifolds? And so basically, it comes from this construction that Alan Weinstein described back in 1991. And basically, in the language of Liouville sectors, what it says is that Liouville sectors can be glued together along their stops. Sorry, stop is another name for what I call this Legendrian. We'll see once I discuss wrapping in the context of Fukaya categories why I'm calling it a stop. But in other words, what this theorem says is that if I have two Weinstein manifolds, M1 lambda 1, two Liouville sectors, maybe Weinstein sectors, whatever, M1 lambda 1 and M2 lambda 2, given an identification of the two Legendrians, which means, an identification of their, like as germs of Legendrians, which means like given an identification of their neighborhoods in the contact manifold, there exists a gluing where I take M1 lambda 1 and glue it to M2 lambda 2 along this lambda 1 equals lambda 2, along a neighborhood of this lambda 1 equals lambda 2. So I'll explain that now in pictures. I mean, just to give a sort of spoiler for where this talk is going to go, or where, either this talk or my next talk is going to go, this paper of Ganatra Pardonshenda I mentioned is called sectorial descent, which means, in other words, it's going to tell you that, like, Liouville, if you have a Liouville manifold or a Weinstein manifold, these Liouville sectors are like the right notion of sort of open cover to consider on that. And that the Fukaya category of this thing is going to be local with respect to that. Like if you glue your manifold from those pieces, from various Liouville sectors, then the Fukaya category will also be glued from those pieces. So that's the theorem that I'm going to state later on. But let me sort of first indicate for now how this gluing works. So let me give an example. So suppose I take, let's just do a very simple example that I can draw in a picture. So I'm going to take two disks and let me take some stops in them, whatever. And I'm going to identify this stop here with this stop here. I'm going to identify this Legendrian lambda 1 with this Legendrian lambda 2. And yes, there's other, each of these manifolds also has other stops that are not going to get identified. So I'm gluing along only part of the total Legendrian in the boundary here. And so what this is going to do is, the way this gluing is going to work is I said, well, okay, so what a Liouville sector is like, this kind of thing, and then I have another one over here. And I have this orange thing. And what I said is that I have an identification of the neighborhoods of these orange things here. Just these two here. So this blue guy gets identified with this blue guy. Essentially what happens is that I glue on a little kind of strip here using that identification. I'll draw a little line like this to indicate that these guys are becoming identified here. So basically what Weinstein's construction says is start with your Liouville domain. So I start with the Liouville domain of this thing. It has some Liouville vector field, as we've discussed, that's like a radial vector field. And then in a neighborhood of each of these stops, these Legendrians, I modify the vector field. So it's kind of turning away from them. And similarly over here, whatever, it's going outwards here, and it's sort of turning away from these stops. And so then what's happening here is that, like, near this stop now, up in this region, he looks like, my Liouville vector field looks like the sort of cotangent vector field to I mean, he looks like the cotangent vector field to, like, T star R, basically, of like this stop times R. So he's and he agrees with the Liouville vector field over here. Yeah. And then, of course, there's also more Liouville vector field over here, and then I still have some stops in the remainder of this manifold. So what I get in the end of this picture is, is telling me that what I've gotten in the end is a disk now with 4 stops on it. So you can see I started with a disk with 3 stops, I started with another disk with 3 stops, and then I sort of glued together these two guys, and I kind of ate that stop, that Legendrian, like both of those Legendrians now disappeared. So I have the 4 remaining Legendrians, but those 2 Legendrians are no longer in the picture. They sort of combine to glue together this manifold. So kind of this result is telling you that the disk with 4 with 4 marked points on the boundary has an open cover in terms of 2 Liouville sectors, right? There's like this. I guess I've drawn the picture here. So this picture is sort of telling me that like I have kind of this Liouville sector here and this Liouville sector here, and they're intersecting along kind of this Liouville sector here. So this Liouville sector in the middle is a disk with 2 marked points. So just to state in sort of words what I just state in pictures what I just said. What I just said is that this thing has a gluing description as a disk with 3 marked points and a disk with 3 marked points glued together along a disk with 2 marked points. So, again, later on in the talk, we'll see that if you wanted to compute the Fukaya category of this thing, you could figure out that it's glued together from the Fukaya categories of this thing and this thing along the Fukaya category of this thing. But, this is, again, just like what it means to take an open cover of a Liouville manifold in Liouville geometry. Questions about this construction? Sort of thinking about the way that you can glue Liouville sectors together is really important. I'm going to give one more example, but I just want, hopefully people are like satisfied with this sort of.
Larry, how does this with 2 points advantage to each of the factors?
So, right. So yeah, the disk with 2 points. So the point is that the disk with 2 points is sort of what's happening. So as a Liouville domain, yeah, what do I want to say here? Now I'm wondering whether I've formulated things in the best way for. Yeah, maybe I don't have anything. Okay, maybe if I say things in the language of Skeleta later on, it might make more sense. But maybe the best thing to do is to kind of see this picture here. That like this picture is kind of telling you that like a neighborhood, basically a neighborhood of this thing looks like that Liouville sector. Sort of, I'm slicing up. I mean, this is telling me that like what I'm doing here is I'm kind of slicing up this disk into 2 pieces, and I'm thinking about what the Liouville vector field is doing on each of those 2 pieces. And the point is that like, yeah, here, maybe let me draw it like this way. Suppose I elongate this this disk so he looks more like something like this. And then I try and sort of slice up this disk. So let me draw what the Liouville vector field is doing here. So the Liouville vector field, is certainly outward pointing out here, and it's kind of downward pointing. It's kind of a, outward pointing like this on this part, and outward pointing like this on this part. And now, so the point is that if I tried to slice up this disk into kind of 2 pieces here, like say I took an open cover where that's like everything to the left of one dotted line and everything to the right of the other dotted line, then if I look at this region between the 2 dotted lines, then what's happening on this region is this is not a Liouville domain, because on this region, my Liouville vector field is like over here, he's pointing like this on the boundary, right? So that if I think of this as like a whatever, the Liouville vector field is not outward pointing on this part of my boundary here. So this is not like, as a Liouville structure, it's not a Liouville manifold, a Liouville domain in the sense I like, but it is a Liouville sector in the sense like the vector field is like, precisely not outward pointing like here in a neighborhood of this guy. So another way to think about what the Liouville sector is that the Liouville sector is telling you about like how you've modified your Liouville vector field in various regions. And again, like a Liouville, when I have a symplectic manifold, I'm okay doing like Liouville homotopies of, like this is a perfectly, this symplectic manifold is equivalent to this symplectic manifold. Like to this symplectic manifold. If I sort of stretch things out and sort of like expand a region where my Liouville vector field is doing this, then like that's what this gluing description is telling me. It's telling me that this guy has a, description of its Liouville vector field where like on one region, he looks like the Liouville vector field of this guy. On another region, he looks like the Liouville vector field of this guy. And in the middle, he looks like a Liouville vector field that is like this. In these pictures, it might be, okay, maybe I should make a definition. The skeleton of a Liouville manifold, a Liouville sector, say, is the set of points which does not escape to infinity under Liouville flow. So if I have a Liouville manifold, so on a Weinstein manifold, so remember, manifold means that I'm not a sector, or I'm a sector with trivial Legendrian. I have no Legendrian at infinity, so I'm only considering sort of the cylindricalization of my Liouville domain. And on a Weinstein manifold just means where you've tamed your vector field, so it's not doing anything crazy. The skeleton is equal to the union of attracting sets of the critical loci of my Morse-Bott function that tames my vector field, or in other words, the zero locus of the I'll call it the critical locus of my vector field Z, the places where my vector field vanishes. So on a example, M, if M is the cotangent bundle of X, then the skeleton of M is probably just going to be X itself. I can take the Morse-Bott function that's just the, that just vanishes on, that just has critical locus given by the zero section. Okay, but for a Liouville sector, what does it mean? I look at all the points that don't escape to infinity, but I allow the points in my skeleton. These things are not infinity, these bits here. Because, again, when I define my Liouville sector, the point is that like, I did this completion away from these points. And so on this point, if I hit this boundary and I'm away from this point, then I'm still going to flow off this way. So I'm still going to flow off to infinity. But if I hit this point exactly, then I won't. So my skeleton in these pictures is going to look something like this in this case, or this in this case. Okay, so the skeleton is like take the sort of compact part of the skeleton and then take this, and then take the sort of like, take the Legendrian at infinity and flow it backwards under the Liouville flow. And so this skeleton is just a helpful like diagrammatic way. I mean, it's much more than that, but it's a helpful way of organizing like what the vector field, what the Liouville vector field is doing here. And so if I sort of draw these skeleton in here, then you can see what's happening better. But here I drew a skeleton like this, but I could equally have drawn it like this. Sort of, I could have massaged my Liouville flow. So here I've taken a Liouville flow that's like totally cylindrical at the, totally whatever, outward pointing at the near zero. And here I've massaged my vector field a little, so it's pointing like up like this for a while and then out like this over here.
You consider those to be the same.
Yeah, so they're homotopic Liouville sectors. So I only, really ever care about things up to Liouville homotopy. So I allow myself to be clear, Liouville homotopies should be, I guess, like compactly supported or something. So just in case I can't do like some crazy whatever, but like certainly like in this case, doing a move like changing my Liouville vector field slightly to like from this one to this one is just a very simple move that's not changing the underlying symplectic manifold. To me. So the point is that near a, like this analogy is supposed to be very sharp, that if your skeleton is smooth, then you're literally the cotangent bundle of your skeleton. And so you should always imagine that like any Weinstein manifold, any Liouville manifold is like a sort of cotangent bundle to its skeleton. So sort of like if I drew a line, like if I drew a, if I, well, I don't know. I guess the point is that, yeah, you can have these, like the fact that this skeleton is singular is saying that my Liouville flow is sort of doing some weird things in some places. But near any smooth point of my skeleton, I literally just look like the cotangent bundle to that thing as far as my Liouville geometry goes. So this is a very helpful way of understanding things.
In the Liouville homotopy, you don't change the ambient symplectic line?
Maybe not, although I'm also okay with changing the ambient symplectic form so long as it remains exact.
I'm just wondering, with the derivative of lambda, let's say lambda is changing in time.
Yeah.
The derivative of lambda would be closed.
Yeah.
Does it have to be exact?
I think I do want that.
Okay.
Yeah. Okay, let me draw another example here that's slightly less trivial, and then it's not just a disk. So suppose I took, say, a T star S1 and another T star S1, and I put one stop on each of them. Maybe I should use a different color for the sort of compact part of my skeleton. Not that it matters, but here's the compact part. It's a similar color, so it's okay. And then I can glue together these things along their stops. So again, what it means to put a stop there is like, I should imagine that I have something like, like this. Yeah, and similarly over here. So this boundary component is what I was drawing in blue before. And then I had this orange bit here. Yeah. So the point is that my Liouville vector field, so down here, my Liouville vector field is doing whatever it was doing before. It's just pointing straight downwards. And over here, it's pointing up, but then I modified it so like on the back end of my cylinder, like far away from this point, it's still pointing up. But over here near this guy, he's sort of pointing outward a little bit like that, right? Because I want him to sort of like near the skeleton, I want him to be pointing like he looks like a sort of like the cotangent flow to this thing. And then I can glue these together by just sort of attaching this little guy here, which again, this is a disk with two stops, sort of basic Weinstein handle attachment. So I'm attaching this disk with two stops here, which again has something that just has Liouville vector field going like, this is the standard sort of T star of 0, 1 Liouville vector field. And so I attach this, and when I attach this, then, well, so I claim that after this attachment, if you stare at it, you'll see that I have produced for you a picture of the symplectic, the Liouville pair of pants. So with my skeleton given by like, I have one circle kind of here, I have one circle kind of here, and then I have this one like orange line connecting those two circles like this. And so my Liouville vector field sort of down at the bottom of these cylinders is just pointing like this. And then there's this extra, boundary component in the Liouville domain, which is like, you follow this guy around here, and my Liouville vector field is pointing outward on that guy everywhere as well. So he's pointing outward like this as well. And then in the interior here, he's pointing like upward, and on the back end, he's also pointing outward from this guy. So over here, everywhere, he's pointing like this. Okay, so this is now we're getting somewhere kind of non-trivial. I mean, before I was telling you, okay, if you want to compute the Fukaya category of a disk with various amounts of stops, it's good to get in various ways. You might say whatever, but okay, this is a non-trivial symplectic manifold, and it's a really important one, right? I think the pair of pants is a manifold that lots of people recognize as important. There's higher dimensional examples as well that sort of follow this same pattern. And what I've just said is that, like, if you understand the Fukaya category of a cylinder with a single stop, which hopefully this is a cotangent bundle, so hopefully we understand it pretty well. If you understand that Fukaya category and you know how to do this gluing, then now you understand the Fukaya category of this manifold here. By just literally this thing we just said is glued together from cylinder with a stop, cylinder with a stop, and it's glued together along this like disk with two stops. Okay, so I am actually able to say some things about the wrapped Fukaya category before our hour is over. So before I say anything about categories, let me stop and ask for any more questions about this, if everything I've said here kind of makes sense to people. Okay. Seeing no questions, I will start to say some things about the Fukaya category, since that was, in fact, the title of my talk. So the way the wrapped Fukaya category is defined of a Liouville manifold or Liouville sector is you first define a sort of non-wrapped version of the Fukaya category. So I know I promised this talk is about wrapped Fukaya categories of Liouville sectors. I'm going to start with a non-wrapped Fukaya category. Let me say that sort of the wrapped Fukaya category is, from my perspective, kind of the correct thing to consider from a sort of categorical perspective. It has very nice categorical properties. This one has very bad categorical properties. I mean, if you're an algebraic geometer, you should think the wrapped Fukaya category is analogous to like the category of coherent sheaves on an algebraic variety. It's a very nice category, whereas this is analogous to something like the category of torsion sheaves or like or properly supported sheaves on an algebraic variety or something. Like the category of skyscraper sheaves on an algebraic variety is maybe not that interesting because you don't have the structure sheaf in there. That's just an analogy that is made precise by mirror symmetry in many cases. Okay, so what is this non-wrapped Fukaya category of a Liouville sector? So I'm going to continue writing m comma lambda for a Liouville sector. So this is going to be m is my Liouville, m is a Liouville domain, and lambda is a Legendrian in the contact boundary. Lambda inside boundary of M. And as usual, I may want this Weinstein condition, although it's not strictly speaking necessary for any of the things I'm going to say, I think. Okay, so this is some kind of category. So the objects are going to be exact Lagrangians, exact Lagrangian submanifolds L inside of M, disjoint from lambda. And I should want L to be transverse to the boundary if it intersects the boundary as well. Or maybe, is that what I want? Transverse. I mean, yeah, I don't want L doing anything bad at the boundary, so to speak. I mean, somehow maybe the right thing to say is that really I should complete M to a, I mean, I should think, if I think of the Liouville sector, maybe I'll just say cylindrical at infinity. So if I think of this Liouville sector as obtained from a completion of a Liouville manifold, then all that means is that like, a completion of a Liouville domain, then all that means is like, here's my Liouville domain. I have a Lagrangian, which inside the Liouville domain is doing whatever. And then out here, once he hits the boundary of that Liouville domain, he just sort of goes straight up in the cylindricalization. So all the information of L is contained in, like outside a compact neighborhood is contained in, you know, where he's hitting the boundary of the Liouville domain. And these are exact Lagrangians. So exact is going to mean that the symplectic form, that the Liouville form restricted to L. So we know that the Liouville form, we know that d lambda is the symplectic form. So omega restricted to L is 0. But lambda restricted to L, therefore, is a closed one form. And the exactness condition on L is that this form actually has to be exact. So lambda restricted to L is equal to df for some function f on lambda, on L. There's a stronger condition you can make, which is that lambda is actually conic for the Liouville flow, that like literally every point of L, like the whole tangent direction of L is pointing along the Liouville flow. And that would be the condition that this f is actually equal to 0. So I won't impose that condition, although you can kind of obtain that by sort of taking a limit as you flow down by the Liouville form. But these are the Lagrangians that for now we are going to be interested in. So ultimately, in the Fukaya category, of course, you might want to consider non-exact Lagrangian submanifolds. That's going to lead to a lot more difficulties. Basically, the nice thing here is that studying like exact Lagrangians in Liouville manifolds is a sort of qualitative or topological thing. Like sort of the Fukaya category is famous for having to, you know, for having involving counts of holomorphic disks, and you have to be very careful about the areas of those disks. And so long as you consider exact Lagrangians in an exact symplectic manifold, you can completely ignore all information about the areas of those disks. So that's what makes this thing sort of very tractable. That's one thing to say. Another thing is that ultimately we'll want to consider more general objects than just submanifolds. At a bare minimum, probably you'll want to allow immersed Lagrangians, right? You might want to allow like a Lagrangian that does something like this. You know, that can be very interesting. You can make sense of that. And ultimately, oh yeah, and then the other thing is, so an object I said is an exact Lagrangian submanifold disjoint from lambda, cylindrical at infinity, plus some extra data, which I'm not going to define precisely, but I'll say plus grading and orientation data. So this orientation data has something to do with like, you might want to choose a spin structure on your Lagrangian. Let me not get into that. It's not so important for any calculation that we're going to do. The grading data is more important, but I'm going to ignore it for the moment and say that, you know, it's important when you try and, you know, if you want to get a triangulated category, for instance, things in the triangulated category have like, you know, different gradings or possibly shifts of grading functors, and you want to keep track of those. So that's important, but again, I'm not going to say it at a first pass of what it is. So okay, so those are what the objects in my category are, and then the hom from L1 to L2. I'm going to assume that so if L1 is equal to L2, then this is just going to compute the cohomology. But I'm going to assume that L1 is transversal to L2. And then the hom from L1 to L2, so they're both Lagrangians. So if they're transverse to each other, that means that they're meeting each other in a set of points, isolated points. And the hom is going to be computed by the Floer cohomology of L1 with L2. So this is you know, the fundamental thing in the Fukaya category. So this is some chain complex with basis given by the set of intersection points of L1 and L2. So I said that if these guys are meeting transversely, then this is a finite set. And where the differential in the chain complex is given by counting holomorphic disks. So the differential, so this is a chain complex. So I told you as an underlying vector space what it is. It has a vector space basis given by one thing for each of these intersection points. I didn't tell you what the grading is, but this grading data determines the grading. So now you have an underlying graded vector space, and the chain complex is a graded vector space with a differential. And if I have 2 points P and Q in this set, L1 intersect L2, but if I have a point P in this set, then I can ask what's the differential of P, like P being a basis element in this chain complex. And the answer is it's a sum over the other basis vectors Q, where I count the coefficient of Q in this sum is going to be the number of the number of holomorphic disks with boundary on Lagrangians L1 and L2 that at one end of this is a holomorphic strip that at one end is asymptotic to P and at the other end is asymptotic to Q, and in the middle satisfies the J holomorphic curve equation. Del bar U is equal to 0. Where del bar is the sort of J, the almost complex structure. So this symplectic manifold has some almost complex structure, and when you study symplectic geometry, you like use that almost complex structure to count some homomorphic disks. Okay, so I know I sort of like this talk was supposed to be about introduction to the Fukaya category, and at the end of my first hour of my talk, I've spent now 1 minute saying what the actual Fukaya category is, and I just told you it's just some BS about blur homology and counting holomorphic curves. I'm going to repair that later. So the point is, I'll just say, so I guess this is about the point where we take our break in the talk, is that right? So I'll just say that like my goal in this talk is to tell you all of these Ganatra-Pardonchendo structural results about the wrapped Fukaya category. And once you know about those structural results, you can kind of forget about all this other nonsense. I mean, it's not nonsense, it's important, but once you know about the structural results, then you can kind of like bootstrap up from calculations you understand. Like you can think about, maybe there's like one disk that you might compute like when you're studying this Fukaya category, but once you know like this Fukaya category, then you can just glue together copies of this disk to get all kinds of other Fukaya categories. So, okay, there's some. I haven't gotten to the wrapped Fukaya category yet either, but I've told you that like the classical sort of non-wrapped Fukaya category is something like I'm considering, Lagrangian submanifolds in my symplectic manifold, exact Lagrangian submanifolds, and I'm trying to, I'm trying to compute some holomorphic disks where they intersect with each other. So just to give a hint of where I'm going in the next section of the talk, the wrapped Fukaya category is about what happens if you have a non-compact Lagrangian. And here's my T star S1. What happens if I have a non-compact Lagrangian like this one? How do I deal with the behavior of this Lagrangian at infinity? If I have maybe. No, I'll end right there, just as a little tantalizing bit for people. So maybe we can take a break now.
Okay, thanks. But we could do another, like if you had in mind to do another section today, then we should do it.
Yeah, well, I can say what I can say what the wrapped Fukaya category is, I guess, since I haven't done that yet. Maybe I should end by saying what the wrapped Fukaya category is. So maybe you tell me a little about the structure of this thing. At some point, there's questions or more discussion.
I mean, if we do questions now, then I'm going to ask things like, okay, so tell us if you have two pieces, what are the categorical things associated to them? If they're glued, what is the result in gluing? In other words, the correspondence and the gluing procedure.
Yeah,
that's what I would be asking you about.
Okay,
that's
so
in your next section.
Well, maybe I guess in my next section I would define what the wrapped Fukaya category is, and then I would start to give some examples.
Yeah, I think it's good to do that. Yeah,
Okay.
to do that.
Okay.
Let's just wait. And then continue.
Okay. Are there any snacks downstairs? Is
There
it
might
tea
be.
time now?
I'm
Maybe I can take this off for a
not
moment.
sure how it's scheduled.
That I should just tell you how to compute the wrapped Fukaya category. But before I do that, I'm not going to do that yet. I mean, it'll happen next week for sure. But like, I should at least define the wrapped Fukaya category. I know that, maybe I don't need to justify everything and I won't justify everything, but like, I should at least tell you what is this thing that we're computing. So I told you what this non-wrapped Fukaya category is. And to define the wrapped Fukaya category, I only need one further ingredient, which is the notion of a positive contact isotopy. So let me say that when I was doing this, like a fundamental thing in Fukaya categories in fluorocohomology is that like sometimes you have Lagrangians that are not transverse, and the way you solve that problem is you do some like Hamiltonian isotopy, like a compactly supported Hamiltonian isotopy. And there's some notion of continuation map that there's some notion of whatever, like that proves that a compactly supported Hamiltonian isotopy is not going to change your fluorocohomology groups. So the question is, what about in a non-compact symplectic manifold with a non-compact exact Lagrangian? What kind of isotopies are you allowed to use at infinity? We say a contact vector field. So contact vector field, I mean a vector field on a contact manifold that preserves the contact structure. So in other words, it's the germ of a contact isotopy, or the derivative of a contact isotopy, some isomorphism of a contact manifold. We say that one of these things is positive if it pairs positively with the contact form. Contact vector field V is positive if it pairs positively with this thing here. So there's a correspondence between positive vector fields on a contact manifold and positive functions, actually, that the Lie derivative of the, if I take a contact vector field, then what it means to be a contact vector field is that if I take the Lie derivative of the contact form, then that's going to preserve it up to multiplication by some function which might be positive or negative. And we say that this is positive if f is if this function f on my contact manifold is positive. So just as an example, on the cylinder, you can kind of check this T star S1, you can kind of check that the positive contact vector fields on this top circle are the ones that go one direction. Maybe I'll use a different color. Just use blue. The positive contact vector fields are the ones that go like this, and on the bottom, the positive contact vector fields are the ones that go in the opposite way. So let S be the set of positive isotopies on the boundary of M. So now I'm returning to this question of I have a Liouville sector. So I'm going to take positive isotopies on the boundary of M. And in the case where I have a non-zero Legendrian, I'm going to require that that isotopy is zero, is doing nothing on the to the Legendrian, which are zero on lambda. So given such an isotopy, so given an isotopy, I'll call it phi sub s. So it's the isotopy corresponding to an element S and S. So given one of these guys phi s, there's a continuation map from, so I'll call this CS, in my non-wrapped Fukaya category from my Lagrangian to its push off by this contact isotopy. So the idea is that like, okay, whatever you know, whatever I'm doing to my Lagrangian, if I have a Lagrangian that like at infinity whatever, then I have if I sort of push it off itself by a little bit of a contact isotopy at infinity, then there's still some kind of intersection point. There's some map in the category from this Lagrangian to a small push off itself. Yeah.
How do you extend the unit manifold? Each circular on the bond.
Yeah, I'm saying that like you can inside of a compact. So a Liouville manifold is like a Liouville domain plus like stuff at infinity, and inside the Liouville domain, which is a compact thing, you can just do whatever you want. You can do any Hamiltonian isotopy, do any like compactly supported Hamiltonian isotopy in there, and then I'm saying like on that, what about isotopies that are not compactly supported? And an isotopy that's not compactly supported has to be like extended from like the boundary of the Liouville domain in this way. So the idea is that a Liouville manifold is like outside of a compact set. It just looks like its boundary times R.
Okay, so
So the idea is if I have a Liouville vector field on here, like say the vector field that's like, you know, rotates this circle by a certain amount, then like that vector field just gets scaled up and up as I go up my cylinder. So as I go up my cylinder, I'm just taking that vector field and I'm scaling the circle more and more as I go up.
so is it function on the growth rate of this?
Well, it's linear. It's linear. I mean, the vector field grows linearly in R as I move up in this direction. So in the original historical approach to the wrapped Fukaya category, what they said was take a Hamiltonian function that's quadratic at infinity. That like your Hamiltonian function is like R squared, P squared or whatever. And then if you take that derivative, then you get a vector field that grows linearly as you go up here. But sort of the more modern approach is just consider the set of all possible positive isotopies. Because you like I can take a bigger positive isotopy too. Just take all possible positive isotopies, and then given phi, there's a continuation map, and then finally the wrapped Fukaya category. So now I can give a definition of the wrapped Fukaya category. Wrapped Fukaya category of M is obtained by take this non-wrapped Fukaya category, non-wrapped category, and invert all of these continuation maps. Okay, so if I have a category and I have a morphism in that category, there's something I can do called a localization, where I formally adjoin an inverse to that morphism. And that's going to force that this object and this object become isomorphic objects in my new category. So that is the definition of the wrapped Fukaya category.
Regarding this range of the chain cards.
Yeah.
So this localization means.
Yeah. I mean, really, I should want to, work sort of, I don't know. But yes. I was going to say, really, I should want to work, I don't know, with stably or something, but sure.
So also in this context, the objects you no longer require cylindrical at infinity. Is that's like the only change from?
No, I still have the same objects. The point is that like this object, like I have the same objects, but now kind of this object becomes identified with like this object where I've pushed it off a little bit, and this object where I pushed it off a little bit more, and this object where I pushed it off a little bit more, and so on. You should imagine that like this vector field is somehow the right way to, well, okay, I guess, I mean, the right way to think about this is that like I still have the same objects, but now when I'm computing the Hom, like, okay, so in here, I have this object here. And when I compute the Hom from this object to itself, the way that I do that is, yes, now I consider an object that's obtained from this one by like formally doing more and more wrapping it around as he goes at infinity. Yeah. Yeah.
So is the point that you now know what the Hom space is between two Lagrangians which don't intersect transversely?
It's not about I mean, if they didn't intersect transversely before, then I could have done a small, compactly supported Hamiltonian to make them intersect transversely. The point was that I didn't know what I was supposed to do about this guy at infinity. Previously, I just had this Lagrangian be like, if I did a small perturbation of it, like I could have taken this and just done a small perturbation like this or something. But now what I'm saying is that like what I actually want to do is that at infinity, I should want to, as I go up this cylinder, the more I go up this cylinder, the more I should like keep wrapping him like this.
So does this mean, if you take a compact Lagrangian in a compact point,
Then nothing is going to change.
but if you deform it by a Hamiltonian isotopy, are you now identifying
Well,
those two objects?
they were already, what do you mean? They were, I mean, they by something at infinity. I mean, an isotopy at infinity won't touch a compact Lagrangian. And already in my original category, a compactly supported Hamiltonian isotopy didn't change my object up to isomorphism for reasons I said before. It doesn't change the Floer cohomology.
Meaning that the continuation map is already invertible.
Yeah, the continuation map, the thing about inverting these continuation maps is really for continuation maps for these isotopies like at infinity. So for like the compactly supported Hamiltonian isotopies, kind of nothing was really changing.
So is the continuation map a morphism in the non-wrapped category?
Yeah, it is a morphism in the non-wrapped category. Like I had a canonical morphism in the non-wrapped category from like my Lagrangian to like my Lagrangian like pushed off itself slightly.
Is it obvious? How do you know which intersection point or what combination of them is this canonical?
It's a bit of a maybe it's a bit technical, and let me not try and say it. Somehow like units in the Fukaya category are always a bit, I mean, there's this PSS map. The point is that like the Floer cohomology of a Lagrangian with itself is like isomorphic to its cohomology. This is called the PSS map, Punikin-Salomon something. Like there's a unit in there. Yeah, there's this, yeah, I don't know, I probably am not going to get this because this is not the way that I think about this very much. So I think it's a bit of a technical thing defining the continuation element. I think the point though is that like if you took a very small isotopy, then you just look like there's a unit in the Floer cohomology. If you take a very big isotopy, like what if I isotope this guy like all the way around or something like that, then the continuation map is like break this into a bunch of small isotopies, and at every step you have a well-defined continuation element. So for those of you who like the theory of constructible sheaves, like there's some, if I have, like there's some correspondence created by maybe Guillermo Kashiwara Shapira that says that like contact isotopies on the boundary of T star M correspond to they have some kind of kernel, which is like some kind of sheaf in like I think M times R. Which is like some kind of kernel which does the which like implements, which you can use to do a sort of like Fourier like a Fourier Mukai, like an integral kernel type thing, which gives a functor from sheaves. Maybe I should say this: a contact isotopy on the boundary of T star M gives you some map from sheaves on M to sheaves on M, constructible sheaves on M to constructible sheaves on M, and you can kind of invert all of those. You can localize your category of constructible sheaves on M by doing that thing. Sorry, I would have to actually give more background in order to say more about this. Let me not try and do that right now.
I think I still don't understand the cylindrical at infinity requirement necessarily. I would have thought these like these things which you extend by continuing to twist were cylindrical.
Yeah. So um uh I mean, I think the point is that, like, again, my Lagrangian itself is cylindrical at infinity, but then when I compute its endomorphism, when I compute, say, the Hom of this Lagrangian with something else, then I'm computing the Floer cohomology of something that now is wrapping at infinity. Like some of the objects in my category are literally Lagrangians that are cylindrical at infinity. But when computing their Hom spaces, I have to do something that involves some infinite amount of wrapping around. Yeah.
Could you explain how when we localize the category, what happens to the morphism?
Yeah.
Understand how it's equivalent to the geometric equation that.
Yeah, so I mean, when you localize a category, right, how do what does it mean to localize a category? One thing that you could say is that like the point is that like now any Lagrangian is identified with its image under this any Lagrangian is identified with its image under this phi s flow. So you can take a I think that the right thing to say is that like I can take a like an object of this is going to be like a formal like object of localized category. If I take a category and localize it some collection of morphisms W, then I think an object is going to like formally be like something where I have a bunch of x0, x1, x2, w0, w1, ... where I have some collection of like elements like this. And then when I compute the morphisms in the category, then I like formally take a colimit over the various morphism spaces that I would have gotten, and that corresponds to like what I would have done by like taking my Lagrangian and comparing it against like bigger and bigger wrappings of my other Lagrangian. Sorry, I don't think I've done a good job of explaining this, but maybe I should just finish this portion of the talk now and we can go to examples or computations or structural properties or something. Let me just do an example. I mean, I've done an example here, sort of, but like. Example. Let me do the cotangent bundle to the interval 0, 1, the closed interval. So that's the same thing as the disk with two stops on it. And so this thing has a skeleton that looks like this. So I can take my Lagrangian to be something like this. Here's my Lagrangian L. And then we said that the contact vector field is positive, like if it goes like this on this part, and if it goes like this on this part. And so what I'm going to find is that like Hom from L to itself in the wrapped category is going to be equal to Hom from okay, now I've forgotten whether my convention is that I wrap the first guy or the second guy. It probably doesn't matter. I mean, it matters, but okay, I'm not going to remember which way it goes. It probably doesn't matter which convention I choose. I mean, so let me say Hom from like L wrapped to L, where L wrapped is going to be this guy. So the point is, what I was saying before is that like I have this, given this Lagrangian L, I have this series of like bigger and bigger wrappings of L, where each wrapping I do is like, deforming me further in the direction of a positive contact isotopy. So I have L, I have a natural continuation to L wrapped, I have a natural continuation to like, let me call like L like double wrapped and L like triple wrapped, where like L double wrapped maybe is like this guy where I've wrapped L even further, etc. And then, formally to compute the HOM of, this guy with something else, I take the co-limit of the HOMs over all of these things, or the limit, depending on, I guess in this case, maybe the limit. But in this case, I can see that like I only needed to wrap L a little bit, and then it's not going to change anything like how much I wrapped it more after that. Like once I've wrapped L a little bit, now he's intersecting the original L like at one point and not going to intersect that L anywhere else. So it kind of didn't matter how much I wrapped after that point. So what I find is that this is equal to just K, my coefficient field. That the HOM from L to itself is just a one-dimensional vector space, because he has a basis given by just this one intersection point. Yeah.
But so these Lagrangians don't appear to be cylindrical at infinity. So how are they?
Oh, they're still cylindrical at infinity. I mean, well, the way I've drawn, I mean, this is my infinity. I mean, how to say, this is my boundary. It's still like hitting the boundary at a certain point. So the point is that if I had a maybe if I had a if I had a cylinder like this, say with no stops, and I started with this L, then the point is like this L, then I could replace it with something that like near the boundary like does goes a little bit, or goes a little bit more, goes a little bit more, like et cetera, does like a whole bunch of stuff kind of near the boundary is maybe kind of one way of thinking about it.
I think this, what you just said, contradict what you said further. Here you're saying you take the Lagrangian in the back thing with the boundary, and then you deform it on vector fields, and then you extend the cylinder for them. But before you said first you extend the cylinder, and then you deform it on the field, which makes it wrap around. Whereas if you first form and then on the cylinder, it wouldn't wrap around.
Well, but I mean, I think I'm trying to say equivalent things, which is like just do more and more wrappings, and there might be some finite amount of wrappings that you need.
So here you're doing the calculation.
I think the point is that you can maybe I should have drawn this like an actual, like this thing is an actual cylinder that goes to infinity, and the point is that like I can do I can do like a bit of wrapping, or I can do more wrapping and more wrapping, and like the more wrapping I do, I'm eventually there's some co-limit over all the possible wrappings. Okay, I feel like I'm not doing a good job of saying this right now. Sorry.
But this example,
Yes.
I just want to make sure what this example actually is.
Yeah.
So this is HOM from L to itself in which category?
In the wrapped Fukaya category of the disk with, this is the wrapped Fukaya category of the disk with two stops. I mean,
Lambda is 2 points.
yeah, this is lambda is 2 points. So another definition of what this Liouville sector is this is the cotangent bundle of the interval 0, 1. So the cotangent bundle of a compact manifold with boundary gives a Liouville sector where the stops come from the boundary of your original manifold. And maybe you should have said this example, but yeah, this is kind of this. I guess I did say this example. This is kind of this example here.
Where you include the boundary Lagrangian fiber as part of your skeleton. Can you just explain what you said about the relationship between the boundary of the base manifold and the stops? Yeah,
the stops are the boundary of the base manifold. So you can see that like this is my like 0, 1. This is my interval here, and that because the Liouville vector field is always going up. The Liouville vector field is always going like away from the base of the cotangent bundle. And so like this tells me that I have a Liouville sectorial structure here.
Okay, and to make the calculation, what you said was, so you seem to have computed the HOM
Yeah,
by applying applying this contact isotopy, which was
Yeah.
extended into the interior.
Yeah.
And applying it successively and taking a limit.
yes, but then I noticed that because I have stops here and here, no matter how much I wrap, my wrapping is eventually going to like die out here. Like my wrapping tells me like, do any kind of wrapping you want like around here.
Stop it, doesn't reach it.
Like this, yes, you're never allowed to wrap anything past a stop. That's why it's called a stop. It's the thing that stops the wrapping.
That's fine. So are you making the calculation in the visible part of the diagram? Or
Yes.
is the extension important?
This is the where I made the calculation. So I made the calculation by like once I wrap, and no matter how much I made the calculation that my HOM with L is never going to change after I do like some amount of wrapping at infinity. Like once I do a little bit of wrapping, it doesn't matter how much I do because I'm never gonna like wrap all the way around to here. So
I'm
it's
saying, I'm just asking this question because people seem to be concerned about what is happening with this Lagrangian in the cylindrical, in the non-compact.
yes,
phase.
but I can see that nothing interesting is happening to it there, certainly.
Because of the stops.
It's because of the stops, correct.
What if we started with the circle instead of the and the cylindrical extension of the the wrapping of the
Yes.
cylindrical extension L
Yes.
would intersect L into the main time.
Correct, yes. So if I did that example, so this is T star S1. So here's my L, and then my sort of like you know, again, there's multiple ways of thinking about this, which is that I could take this sort of successive colimit or whatever, or I can think about it, yes, that L is sort of like that I want to ultimately like consider the so like HOM of L with itself in the wrapped category is going to be equal to HOM of okay, depending on of this like L prime with L in the sort of is going to be the Floer cohomology. I'll say it this way. It's going to be the Floer cohomology of this L prime with L. But again, that you know, like okay, maybe it was wrong of me to like introduce things this way. I mean, this is the form, but this is the correct formal way of doing it. I mean, the formal way of doing it is to say that like this L prime is represented in the sort of like unwrapped category by some like infinite sequence of these things, and this thing is really like some colimit of like L with L wrapped over whatever's. Let me just not worry about that.
This case, from L to L in the wrapped category is infinite.
Yes. So in this case, what we're going to find is that the HOM from L to L in the wrapped category is going to have a basis given by it's going to be a vector space with a basis given by the integers, which are counting the intersection points of this thing. So there's going to be a vector space with L intersect L prime.
And is this calculation one that you can also do in the Liouville domain, in the Liouville sector?
What do you mean?
What I mean is, if you take this cotangent bundle
Yeah.
and replace it with the codisk bundle.
The Liouville domain. Well, it's sort of.
Calculation you can make there.
I mean, sort of, in the sense that like I mean, I mean, I kind of drew this picture before, but I feel like this is the better way to understand what the calculation is. This is sort of telling you that well, okay, let me say, I can say a little more about why I phrased things this way, which is okay, so this is so next week when I give a talk, it's going to be all about structural properties of this category. And one structural property it's going to have is that well, so let me first do a version of this calculation where I put some stops in. So suppose I put a stop here and I put a stop here, and now I'm interested once again in computing and L is still a cotangent fiber. I said it had to be disjoint from stops. So it's some other cotangent fiber aside from this stop here. So the skeleton of my manifold now, just to keep that in the picture, is this. So I want to know what is the Hom of L with itself. And now I can see if I kind of unwrap this diagram a little bit. Sorry, unwrap in a different sense. I mean, this is like a cylinder, and I'm just going to draw it like this cylinder. This is a fundamental domain of the cylinder where I identify these two ends to make a cylinder. And here's my Lagrangian L. Then I can see that this calculation that I'm going to do here is just the same as this calculation here, right? From the perspective of L, like he doesn't know that these guys are joined up to a cylinder since he's never allowed to wrap past them. He's going to wrap a little bit, he's going to wrap in the top and in the bottom, and he's going to wrap like this. And what I'm going to find is that the endomorphisms of L in this category, in this wrapped category, partially wrapped category, are one-dimensional. And now the point is that, I can imagine that there's like, let me draw a different picture now that's a different fundamental domain where this guy is in the middle.
To pedantry, but end sub.
This is wrapped of T star S1 with stops lambda equals like, the cosphere bundle to a point in S1. Sorry, this S star 1 means like the cosphere bundle to some point, maybe P in S1, which means like the two cotangent directions above this point. This is a point P. Yeah. So now one thing I notice is that kind of like the difference between the fully wrapped Fukaya category of T star S1 and this wrapped Fukaya category is that like, if I take this Lagrangian here and like in the I could take this Lagrangian here and I could take kind of this Lagrangian here. So these are two different Lagrangians, and they have a Hom between them. And the difference between the wrapped Fukaya category, the fully wrapped Fukaya category, and the wrapped Fukaya category with a stop is that in the wrapped Fukaya category, I'm going to say that these two Lagrangians are the same. Right, like my definition of the wrapped Fukaya category was precisely that I did some like localization of the category that said that like if you wrap a little bit, then you don't change what your object is. I would have to do the same thing with down here too. But so the point is that like the wrapped Fukaya category of the wrapped Fukaya category of T star S1 is going to be obtained from this wrapped Fukaya category of T star S1 lambda also by some localization, which is like wrap past the stop. I'm inverting that guy here. So the idea now is going to be that once I know that I can wrap, once I know like this fact, then I can say that, okay, to compute the wrapped Fukaya category of T star S1, let me actually just compute this partially wrapped Fukaya category, which doesn't have that many Lagrangians in it, and then let me compute the fully wrapped Fukaya category afterward.
So, okay, so is it doable?
Yeah, so okay, so I've almost computed this category. I wrote down one Lagrangian and computed its endomorphisms. It turns out that this Lagrangian is not going to see everything in the category. Let me call this Lagrangian L1. There's another Lagrangian L2 that I might want to consider, which is Lagrangian that sort of goes down and then like fully does like a full circuit of the circle. And then goes down like this. So this is my Lagrangian L2. So my Lagrangian L2 is very similar to L1, except he winds once around the circle. And okay, by the same reasoning as for L1, I'm going to find that the endomorphisms in this partially wrapped category, T star S1 lambda of L2, is also equal to K.
Is L2 object in that category?
Why not?
So it decides this.
Why not?
No, it doesn't intersect the stop. The stop is just at infinity. Yeah. I mean, everything has to intersect this guy. Somehow, like, what we'll see is that, like, there's a theorem that kind of the generators of this category is like precisely like the things intersecting the skeleton in various ways. Like, in order to see the whole category, you just have to see all the different parts of the skeleton, because those tell you all the different parts of your manifold. So the endomorphisms of this guy is also a copy of K, for essentially the same reason as we did before, because, like, you know, he can't wrap it all at infinity. So if you can't wrap it all at infinity, and since he's topologically a disk, you're just going to get something that is not that exciting. And then then I just need to compute the Homs between them. And so the point is that if I did this, then what I'm going to find is that, okay, let me draw this picture bigger. So my claim is that the Hom from this L2 to L1. So my claim is that Hom from L2 to L1 is going to be 0, for the reason that I can if L2 starts on the wrong, it starts and ends on the wrong side of L1. So the point is that kind of here, okay. Let me see how this works. Here's my L1, and here is my here's my L2. So he's down on the back side, and then he comes around. Oh, sorry, maybe that's not what I wanted L2 to be. Sorry, let me change this picture slightly. I mean, this is approximately what L2 is going to be after wrapping, but I think I just wanted L2 to be here. Let me draw the picture like this.
You kind of want L2 to be another contention fiber, depends which side.
I want L2 to cross over at some point. So I want L1 to look like this. This is my L1. And I want L2 to look like this, maybe. Maybe that is what I had L2 doing before. So the point is that Hom from L2 to L1 is going to be 0. Okay, maybe something is going to depend on my conventions. But the reason for this Hom is going to be 0 is roughly speaking that I can wrap L1, and that when I wrap L1, I can like wrap him around so that he becomes disjoint from L2. I can wrap L1. I can wrap L1 to like this thing here, so he becomes disjoint from L2. Or wait, can I do that? No, maybe not. So the claim is going to be that I can wrap L1 so it becomes disjoint from L2, but that the Hom from L1 to L2 is going to be a two-dimensional vector space, because like after wrapping, I'm going to have unavoidably I'm going to have like two intersection points between L1 and L2. And
Maybe if you put L1 on the left side,
yeah,
straight down.
yeah. If I put L1 here,
Yeah, so that it hits on the bottom too.
yeah,
And I think that'll work.
yeah. So like one direction of wrapping, I'm going to have like unavoidably two intersection points, and then the other direction of wrapping, I'm going to be able to like make them disjoint from each other. And now the point is that after I do this this localization, so anyway, this tells you that the category of the wrapped Fukaya category up to a generation fact, which I didn't say so far, but this tells you that the wrapped Fukaya category of T star S1 with this stop lambda is equal to the category of a pair of vector spaces V and W with two maps between them. In that like this category I claimed is generated by these two objects, and these two objects, the Homs between them are governed by this quiver, that each one of them has a one-dimensional space of Homs to itself that's just, you know, scalar multiples of the identity, and then there's a two-dimensional space of Homs from one to another. And then finally, the fully wrapped Fukaya category of T star S1 is going to be equal to a certain localization. And what's the localization? It's precisely the localization that says that like each of these maps between them is supposed to become an isomorphism, because I'm allowed to now wrap S1 like past the, each one of these maps failed to be an isomorphism before because of the stop. So if I get rid of the stop, that precisely that localization forces each one of these maps to be an isomorphism. So the wrapped Fukaya category of T star S1 is equivalent to the category whose objects are like a pair of vector spaces together with two isomorphisms between them, which is equivalent to the data of like a vector space with one isomorphism to itself, which is equivalent to the data of a module over the ring K adjoin XX inverse. Yes, I mean, this whole thing is mirror symmetry. So this quiver here, this first category here is equivalent to coherent sheaves on P1. This is what's called the Bailenson exceptional collection for P1, presents coherent sheaves on P1 as modules over this quiver. And then this localization I'm doing is precisely the localization where I'm killing the cones on these two morphisms, which turn out to be the skyscraper sheaves at 0 and infinity. So if I take the category of coherent sheaves on P1 and I quotient by skyscraper sheaf at 0, skyscraper sheaf at infinity, then I get the category of coherent sheaves on P1 minus 0 infinity, which is also called the category of coherent sheaves on C star, which is modules over this C adjoin XX inverse.
So I'm not explicitly asking about the general generation criterion, but let's just look at the stopped category.
Yes.
The one you started with.
Yes.
Right? How many objects, how many different objects, non-isomorphic objects, or how many different objects are there besides L1 and L2?
Well, I mean, I don't even know how to answer the
I
question.
mean, you could have a Lagrangian that intersects.
So I really, when I describe my objects, I said it's a Lagrangian with some extra data. I should have included in that data, the Lagrangian should carry a local system on it as well. So of course, like a local system can have, you know, monodromy, and on a circle, it can have lots of different kinds of monodromy. So, you know, you could take just a circle with different monodromies, but well, let me answer the question in a different way. Let me say what the generation statement is in this case. So the generation, so if I have a Lagrangian, I mean, I'll maybe don't have time to state this very formally, but if I have a Lagrangian skeleton, then the category, wrapped Fukaya category, is generated by co-cores and linking disks. So let me say what a linking disk is. Well, I'll just draw a picture. So what is a linking disk? I have a Legendrian at infinity. This is all taking place inside of a 2n dimensional manifold. The Legendrian is n-1 dimensional. So an n-dimensional thing is the right dimension to link it. So like literally sorry, let me try it this way. I just take a little disk here that's linking my Legendrian. So those are the linking disks. And a co-core you should imagine is also just sort of a linking disk, except it's a linking disk that's linking the like part of the sort of compact part of the skeleton instead of the non-compact part. So like a co-core for a manifold is just going to be a cotangent fiber like this. So this Fukaya category W is generated by these three objects then. It's generated by a cotangent fiber, which is the co-core to this compact part of the skeleton, and then it's generated by these two what are called linking disks. And you know, so let me give these guys names. Let me call this like L. This is my L1. Let me call this D1 and D2. I chose a slightly different generating set over here. I generated by L1 and by L2, and L2 is related to L1 by so L1. I had these two different maps from L1 to L2. Maybe it was from, yeah, I had these two different maps from L1 to L2, and they sat in an exact triangle with these linking disks D1 and D2. So instead of generating by L1, D1, and D2, I instead generated by L1 and L2 because I know that L2 is an exact triangle with L1 and both of these guys. So if I had L1 and L2, then I could get both of these linking disks.
Those are the first map on the first and second one. That first map are the two different maps.
These are the two different maps. That's why I get two different things that fit into an exact triangle. And then the linking disks are the things I quotient when I remove a stop. So the fact is, I'm stating all these structural properties really fast right now. I'll state them again next week more slowly. But the wrapped Fukaya category of M is equal to wrapped Fukaya category, let me say M lambda prime. If I have lambda prime is like a closed subset of M, well, I'll just state it this way. Wrapped Fukaya category of M is equal to wrapped Fukaya category of M lambda quotiented by linking disks to lambda. So I'll sort of justify that next time. But you know, the way you can compute the wrapped Fukaya category then is like I have these objects which are the linking disks, and these are precisely the things that go away when you allow it to wrap past a stop. Like once I allow to wrap past a stop, I make this map an isomorphism, which says that like the cone on this map, the third thing in the exact triangle, has to become 0. Or in other words, this linking disk, once you get rid of the stop, you can just isotope it off itself by a wrapping, and then it's going to have HOM 0 with itself. So it has to be the 0 object. Yeah.
So I'm confused by this commutation of HOM L1, L2, and L2, L1.
Yeah.
I get that like the point that we're only using positive iso is
Yes.
basically saying if we were to continue to shift L2, it's still going to intersect L1 twice, no matter how much we twist.
Yeah.
But because we're like in a localization, shouldn't we still have the maps in the original category? So like HOM L2, L1.
Well, no, but it becomes 0. I mean, the map will become 0 after you like if you go far enough in this diagram, it stabilizes at 0. Like if I try and compute the co-limit of some diagram of a filtered co-limit that like eventually stabilizes at 0, then I'm just going to get 0, or the filtered limit or whatever. Then I'm just going to get 0. Like you might say like, oh, you might say like, oh, this it looks like this guy intersects this guy twice, but after my continuation map, he no longer intersects him, and so he becomes 0. That's sort of what the localization does. Like when you do that localization, it can force some maps to become zero that were not previously zero. I mean, that's kind of what I'm saying here is that this localization is literally a quotient. Like it's forcing the identity maps on certain objects to become zero. Like you might have thought like, oh, well, D1 and D2 still survive as objects in the sort of wrapped Fukaya category, in the fully wrapped Fukaya category. And the answer is, yeah, they do. I mean, they're exact Lagrangians, but they become the zero object in the category now because their identity morphism becomes zero because like I've identified their identity map with the zero map. So it's kind of an algebraic thing. Yeah.
So the non-wrapped Fukaya category is not closed undertaking mapping codes of say L1 and L2, right? So like this makes it look like the wrapped one has more objects than the non-wrapped one because D1 and D2 don't exist in the.
Well, no, I mean, it's not that it has more objects, it's that it has more maps. I mean, I didn't have both of the maps from L1 to L2 before necessarily.
Oh.
Like it depends on how I was doing this, but previously, like in the non-wrapped Fukaya category, depending on whether L1, like I could have chosen L1 to be this thing that was disjoint from L2, in which case they would have had no maps in either direction, or I would have chosen L1 to be this thing that like touches it twice, in which case they would have had two maps in each direction. But yeah. But somehow the correct thing is this wrapped category where it's sort of asymmetrical here.
Okay, so you've given us an example of how to compute the fully wrapped, in other words, no stops, by introducing a stop and then determining somehow what the determining some morphisms that later get inverted into localization, and so you end up with this no stop.
Yeah, so I'm not saying this is necessarily the best way to compute a wrapped Fukaya category, but I'm saying that this is, this example illustrates a lot of structural features here. So I'm sorry for I confused everyone with the actual definition of the wrapped Fukaya category, but I did this example, and if you meditate on this example over the course of the next week, then when we reconvene, I'll sort of give more explanation about all the structural features that made this example work. And about the gluing results that I promised. I mean, this was just a cotangent bundle, but like ultimately the point is maybe I'll give one more example really quickly as long as everyone's still sitting here, which is that if I wanted to know what's the Fukaya category of a punctured elliptic curve, so this is an exact symplectic manifold, and it has a skeleton that looks like this. So I can take as a skeleton, like this is a ribbon graph for the genus 1 curve with one puncture. It looks like sort of two circles intersecting like this. And if I think about what this skeleton is, this skeleton is obtained from, I start with my skeleton of the cylinder with the two mark points, and then I do a little Weinstein gluing to glue together this bit and this bit in the Liouville sector to obtain an actual Liouville manifold. So this is saying that this Liouville manifold is obtained by gluing this Liouville sector to itself along its boundary. And now my gluing theorem tells me that, so in other words, well, my gluing theorem now tells me that the wrapped Fukaya category of this punctured curve is equal to the gluing of this cylinder with the two marked points glued to itself. What is this? This is equal to, well, we just did this calculation that this wrapped Fukaya category was equal to coherent sheaves on P1 glued to itself. And what does glued to itself mean? The thing I'm gluing along turns out to be the structure sheaves of the skyscraper sheaf at 0 and the skyscraper sheaf at infinity. And what I end up finding is this is equal to coherent sheaves on P1 with 0 glued to infinity, which is equal to coherent sheaves on a nodal elliptic curve. So this is another example of how you might do mirror symmetry, is you might say, oh, I have this punctured elliptic curve. How can I compute its Fukaya category? Oh, I see it has an open cover by Liouville sectors, namely this Liouville sector and the Liouville sector that is just like, that's just the T star of the interval. And let me glue together those two Liouville sectors. And that gluing diagram is going to match up with a gluing diagram that identifies coherent sheaves on the nodal curve by taking coherent sheaves on P1 and gluing those 2 points together.
When you work out the Fukaya category of these stopped Liouville domains or Liouville sectors, do you always get categories as opposed to, let's say, A infinity categories, etc.?
Oh, no, you might get A infinity categories.
What are you expected to get, actually?
Well, I don't see, to me, category, I mean, to me, category is synonymous with A infinity category. I mean, they both just mean category to me.
I'm just wondering where it lands, the stopped things, where do they land? A infinity categories, DG categories.
Sure.
How should we think of what the?
However you like.
No. So I can't choose from an empty set. So what are the options and what should I think about where it lands?
Well, so the unwrapped Fukaya category, I guess as I've defined it on the board here, the unwrapped Fukaya category was an A infinity category. I mean, I didn't define the the structure, the composition maps, but they came from counting holomorphic disks. So that was an A infinity category. I mean, and then I took a localization of that, and maybe but that, just to me, like as a person, A infinity category just means category. Like an A infinity category is a category that's associative up to homotopy, but like if you believe that everything in life is up to homotopy, then you never say the words up to homotopy. So an A infinity category is a category with composition that's associative. That's what a category is. So to me, that's why those two words like are the same. But yeah, I mean, if you maybe have a particular model that you really like, if you want to stick to like in that model, then you start with an A infinity category and then you localize it.
Okay, but maybe you can sympathize with me because you're saying coherent sheets rather than derived category.
Oh, sorry, derived
Rather
sure,
than-
derived category of coherent sheaves. Everything is always derived for me. DB code.
Okay, and then, if I go down this road, I would also say, well, okay, bounded in both directions. Is it quasi-coherent or rather, you know what I mean? Like, there's so many different options of what these categories could be. And what I'm wondering is the partially wrapped ones, do they land in something that is tractable?
Yes. I mean, again, this is okay, depending on, what you mean by DB code, this is a true statement here. I mean, that you should think of a partially wrapped Fukaya category as something that under mirror symmetry is expected to correspond to like bounded derived category of coherent sheaves on something. Maybe. I mean, maybe a fancy way to say that is that the wrapped Fukaya category. Am I going to get this right? I think the wrapped Fukaya category is smooth in the sense of non-commutative geometry, as is the category of coherent sheaves. I know this is a singular variety, but the category of coherent sheaves on a singular variety is actually smooth. So the category of perfect complexes that's not smooth. That was probably not helpful to anyone.
Can you just quickly recap again what the categorical advantages were of the Fukaya category for the non-wrapped one?
Well, I would say it's it's a smooth category. So the point is that let me put it this way: for if you what do I want to say? in this case, if you have these stops, then somehow the wrapping was not that important because this category was somehow kind of fully stopped. But in general, like without the stops, if you consider, let me say, suppose you were considering a category of only compact Lagrangians, so you don't want to deal with anything. Suppose you don't know what's happening, what to do at the boundary, so you say, okay, I only want to deal with compact Lagrangians. So inside the Fukaya category of T star S1, which, as we said, looked like the category of coherent sheaves on C star, compact Lagrangians. So maybe let me put it this way: corresponded to like modules over C adjoint X inverse. Compact Lagrangians corresponded to finite dimensional modules. And so you can ask, which category has nicer properties? The category of finite dimensional modules over this algebra, or the wrapped Fukaya category of T star S1 corresponds to the category of perfect modules, which means like essentially, modules that have a, finite, that are constructed but have a like finite resolution by finite free resolution of this thing. And like that's a lot nicer because it contains this ring itself as a module over itself, whereas this category does not. Like the category of finite dimensional modules over this thing is just everything of the form like C adjoint X plus or minus X minus, lambda to the K or whatever. I mean, some for some values of whatever. So these are all the finite dimensional modules over this ring, which are not that exciting. Whereas the category of like perfect modules over this ring includes the ring itself. So that's much better because like that object generates the whole category. Like this category clearly does not have nice categorical properties.
The perfect modules, you said they have a finite length
I mean,
resolution by free,
yeah, I mean, yeah, it's
they're coherent sheaves.
yeah, I mean, so this is a smooth variety. So perfect and coherent mean the same thing.
I see.
So the point is that the category of coherent sheaves, this is about the category of coherent sheaves on C star versus the category of torsion sheaves on C star. Or the category of, skyscraper sheaves on C star. And like the category of torsion sheaves on C star is just not that great of a category. It doesn't have the structure sheaf.
And what about quasi-coherent sheaves?
Well, that formally, so okay, coherent, as I said, coherent sheaves on C star is equivalent to perfect complexes on C star, whatever these two things are synonymous to me. I mean, not just to me, to anyone. I mean, this is just a fact about C star is a smooth variety. So, and QCO for any sort of sufficiently nice space, certainly for any variety that you'll ever encounter in your life, QCO of X is equal to ind of perf X. So there's some sort of algebraic procedure for given a category like this, a small category, for enlarging it to a big category by formally adjoining filtered colimits. And this is this ind construction. And you can go back and forth between these by perf X is equal to, I start with quasi-coherent sheaves on X and I take the compact objects inside of it. So again, there's some sort of categorical criterion for like what it means for an object to be compact. It means it commutes with filtered colimits. I mean, it's HOM with it respects filtered colimits.
Apply this ind construction to the Fukaya category, and that's.
Yeah, I'm saying that like you should think that you got QCO as well because QCO is can be formally recovered from this category.
But there's not a separate geometric interpretation for what that is. On the Fukaya side, it's just you're just saying apply this algebraic procedure.
Yeah, I would say that like I would say that it's sort of like there's a nugget of geometric thing that happens, and then there's various sort of formal nonsense that you can apply to that geometric thing.
Okay, thank you for answering.
Okay, I'm sorry, I've run over. Maybe that's a feature of this seminar. Sure, yeah, and so as I said, okay, so next week I'll maybe do a little more basic example of what I meant by the wrapping stuff, but I'll hopefully at that point, just give state formally all of these categorical properties I was referring to, the Fukaya category, and do more like examples like this of how you can use it to compute things.
Great, thank you.